Hello everyone, my name is Adeline Wiharja, and I will be presenting to you my work on Posable Tensegrity-Constrained Inflatable Kinematic Graphical Analysis. This work is a collaborative effort with Dr. Alexander, Dr. Kim, Professor Brei, Dr. Luntz, Laura Jenner, Alan Kim, and Kunj Patel. Inflatables have been used in a lot of applications in the structural, aerospace, medical, and sports fields for a long time because of their advantages of being low cost, lightweight, and their ability to compactly store and deploy. These traditional inflatable fields, however, all share the same idea that the shape of the fully inflated device is constant. Recently, the soft robotics field has added active shape change to inflatables' otherwise static functionality. This functionality, however, required complex multi-chamber structures and active pressure control that sacrifice many inherent advantages of the inflatables, including simplicity and stowability. Many user interactive commercial devices require only passive shape change or posability, where the users manipulate a device manually and the device simply holds its new posed shape. This paper explores a new approach using internal string-like tensile elements to provide posability or passive shape change while maintaining stowability and other inherent advantages of inflatables, leveraging concepts in the field of tensegrity mechanisms. Tensegrity-constrained inflatables, or TCI in short, is a combination of string tensegrity elements and inflatables. These TCIs can add not just structural support but also additional functionality such as posability. Posable tensegrity-constrained inflatables can change its shape if manually positioned and reshaped by external forces. Even after the forces are removed, it retains its deformed equilibrium shape and position. The operation of this device relies on the interactions of friction between the strings and the loops at end caps. In this illustration, the string configuration only allows bending possibility. When an external bending force is applied, the strings can thread, and the friction between the strings and the loops allows the inflatable to retain its now deformed equilibrium shape and position. This friction-reliant mechanism not only enables passive operation, but also retains the simplicity of inflatables. These posable structures consist of a compliant inflatable bladder with rigid end caps connected by inextensible strings as the tensegrity elements. The compliant bellow-style bladder is fabricated using a novel multi-layered masked heat sealing process, which enables direct fabrication of highly complex and multi-layered structures. One bellow unit is fabricated using bladder sheets and a masking sheet that does not stick to the bladder material when heated. To create one bellow unit, we overlay the two bladder sheets with a mask in between. These three sheets are heat sealed together in a heat press. The bellow regions with masks do not seal to each other and the mask can be taken out of the bellow. This will form this cavity for air, while the rest seal to each other and is now airtight. We can repeat this process to make and attach each bellow unit over many layers, enabling direct production of a complex and customable structures consisting of any desired number of bellow units. To create a full inflatable device, the fabricated bladder is then sealed to the end cap around its edge. To analyze the kinematics and facilitate the design of new posable tensegrity-constrained inflatables, we developed graphical instantaneous center analysis techniques, which is an extension of the traditional linkage IC analysis to also include kinematics of threaded strings. Based on these techniques, we developed several building blocks of posable tensegrity-constrained inflatables in 1 degree of freedom and 2 degrees of freedom motion. A prototype implementing building blocks of posable tensegrity-constrained inflatables in 1 degree of freedom is demonstrated. The simplest 1 degree of freedom building block is bending building block. When the bladder is inflated, the strings will become tight and additional pressure applies tension to the strings. Threading between the loops and the strings will enable the structure to be manually posed over a full range of bed positions, where internal friction between the strings and the loops hold the structure in any intermediate bending position. Here, the inflatable can bend left and right. The compliant motions but not posable are shear in all directions and bending front and back. The next configuration of 1 degree of freedom building block is shearing. This configuration is designed to shear horizontally and can be pushed to either side, left or right, and remaining stably in this shifted position. It can be fully sheared, but friction also holds the structure at any intermediate sheared position. The other degrees of freedom, such as bending in all directions and shear front to back, is compliant but not posable, and inflatable springs back to its initial equilibrium position. These 1 degree of freedom building blocks can be combined to build 2 degrees of freedom building blocks. The first configuration is planar bending and shearing 2 degree of freedom. This particular configuration can be bent and sheared in the same plane. It can be pushed horizontally left and right and remaining stably in this position. It can also be bent, and the 2 possible degrees of freedom can be applied simultaneously. At this new equilibrium position, the bladder deforms to follow the motion of the upper end cap, eventually restricting the range of motion when it becomes stretched. The two 1 degree of freedom bending building blocks can be combined to create bending in 2 degrees of freedom. This gives rise to a 3-dimensional motion. This configuration can be bent around 2 axes, right and left, and also front and back. Here, the 2 possible degrees of freedom is applied separately. It can also be applied simultaneously, resulting in a kinematics like a ball joint, and it stays stably in any combination of bent position. When the inflatable is sheared in any direction, it springs back to its neutral position. Bending and shearing building blocks can also be combined to create 3-dimensional bending and shearing motion. This configuration can be pushed to either side, left and right, and also independently bent to the front or back face. The bending and shearing is applied separately here. The 2 motion can also be applied simultaneously, resulting in a coupled motion. When the inflatable is sheared front and back and bent left and right, the motion is compliant but not posable, and the inflatable will spring back. I would like to thank the General Motors and University of Michigan Multifunctional Vehicle Systems Collaborative Research Lab, and thank you all for listening.